You think space is empty. Look up at the night sky. Between the stars, between the planets, between you and the moon, there's nothing. A vacuum, empty space. That's what it looks like. That's what it feels like. And for thousands of years, that's what everyone believed. But here's the problem with that belief. It's completely wrong. And when you dig into what space actually is, when you understand what physicists discovered in the 20th century, you realize that the idea of empty space is not just wrong, it's impossible. Space cannot be empty. Not because there's dust floating around, not because there are stray atoms here and there, but because of something much stranger, much more fundamental. Space itself is not nothing. It's something. And that something is doing work, constantly, everywhere, even in the darkest, coldest, most isolated regions of the universe. Richard Feynman understood this better than almost anyone. He spent years developing the mathematical tools to describe what's really happening in the vacuum. And what he found was so bizarre, so contrary to common sense, that even now, decades later, most people have no idea just how weird empty space really is. Let's start with what seems obvious. You look around. You see objects. A chair, a table, a person. Those things are made of atoms. Between the atoms, there's space. Between the molecules, space. Between you and the wall, more space. And if you keep zooming out, past the atmosphere, past the moon, past the planets, you get to regions where there are no atoms at all, no particles, no matter, just emptiness. That's what we call the vacuum. And for a long time, people thought that was the end of the story. The vacuum is nothing. It's the absence of stuff. It's the background against which real things exist. But then physics started making progress, and cracks appeared in that simple picture. The first crack came from light. Light travels through space. You can see the stars. You can see the sun. Light is clearly moving from there to here. But if space is truly empty, how does light travel through it? In the 1800s, physicists thought there had to be something filling space, some invisible medium that light waves could ripple through. They called it the ether. Solid objects need something to push against. Sound waves need air or water to propagate. So light waves must need something too, right? They spent decades trying to detect the ether, trying to measure how Earth moved through it. And they found nothing. The famous Michelson-Morley experiment in 1887 showed that there was no ether. Light didn't need a medium. It traveled through empty space just fine. This was shocking. It violated intuition. Waves are disturbances in something. Water waves disturb water. Sound waves disturb air. But light waves disturb nothing? That made no sense. Then Einstein came along with special relativity. He said, forget the ether. Light doesn't need a medium because light is not a wave in a substance. Light is an oscillation of electromagnetic fields, and those fields exist everywhere, even in empty space. This was the first hint that space is not nothing. Space is filled with fields. Now, what's a field? This is where things get tricky, because fields are not objects. You can't touch a field. You can't see it directly. A field is a property of space itself. Every point in space has a value assigned to it. For an electromagnetic field, every point in space has an electric field strength and a magnetic field strength. Those values can change. They can oscillate. They can carry energy. And when those oscillations move through space, we call that light. So even in a vacuum, even in a region with no particles, no atoms, no matter, the electromagnetic field is still there. It's not zero. It's not absent. It's present. It's real. And it's capable of doing things. That's the first step toward understanding why space is not empty. Empty would mean nothing is there, but fields are there. Always. Everywhere. You might say, okay, fine, fields exist in space. But if the field values are zero, if nothing is oscillating, then it's effectively empty, right? Wrong. And this is where quantum mechanics enters and destroys any remaining notion of emptiness. In classical physics, you could imagine a field sitting perfectly still at zero value. No oscillations, no disturbances, just a flat, calm field. But quantum mechanics doesn't allow that. Quantum mechanics says you cannot have a system with precisely zero energy. There's a principle called the Heisenberg uncertainty principle. You've probably heard of it in the context of particles. You can't know both the position and momentum of a particle with perfect precision. But the uncertainty principle is more general than that. It applies to any pair of variables that are related in a certain mathematical way. And it turns out the value of a field and the rate of change of that field are such a pair. If you try to say the field is exactly zero, perfectly still, you're claiming you know both its value and its rate of change with infinite precision. Quantum mechanics says no, you can't do that. There has to be some uncertainty, some fuzziness. And that fuzziness manifests as fluctuations. Even in the vacuum, even with no particles present, the fields are jittering. They're fluctuating up and down, not because something is disturbing them, but because the quantum rules don't allow them to sit still. This is called quantum vacuum fluctuation. And it's not speculation, it's not philosophy, it's measurable. There's an experiment called the Casimir effect. You take two metal plates and place them very close together in a vacuum. According to classical physics, nothing should happen. There's no matter between the plates, there's no force. But in reality, the plates attract each other. Why? Because of vacuum fluctuations. The electromagnetic field between the plates is constrained. Only certain wavelengths of fluctuation can fit in that narrow gap. Outside the plates, the field can fluctuate at any wavelength. So there's more fluctuation pressure pushing the plates together from the outside than pushing them apart from the inside. The plates move. This has been measured. The force is tiny, but it's real. The vacuum is pushing on physical objects. Think about what this means. You have two metal plates in a perfect vacuum. No air, no particles, nothing between them. And yet they feel a force. The emptiness is not empty. The vacuum has structure. It has energy. It's doing work. Feynman was one of the architects of the theory that explains this. It's called quantum electrodynamics, QED for short, and it's the most precisely tested theory in all of physics. QED describes how particles and fields interact at the quantum level. And one of the key insights of QED is that the vacuum is not a passive stage. It's an active participant. In QED, you don't just have particles sitting in empty space, have particles constantly interacting with the vacuum. Let me give you an example. Take an electron just sitting there, not moving. In classical physics, that electron is simple. It has a charge, it has a mass, it sits there. Done. But in QED, that electron is constantly emitting and absorbing virtual photons. Virtual photons are fluctuations of the electromagnetic field. They pop into existence out of the vacuum and then disappear almost immediately. They're not real particles in the sense that you can catch them or measure them directly. They exist for such a short time that they're allowed to violate energy conservation temporarily, thanks to the uncertainty principle. But even though they're virtual, they have real effects. They change the properties of the electron. They affect its mass, its charge, the way it interacts with other particles. You might think this is just theoretical abstraction, but it's not. We've measured these effects. There's something called the Lamb shift. It's a tiny difference in the energy levels of hydrogen atoms that can only be explained by vacuum fluctuations. Classical quantum mechanics, the kind developed in the 1920s, predicted one set of energy levels. But when physicists measured them carefully in the 1940s, they found the levels were slightly off. The difference was tiny, but it was there. And the only way to explain it was to include the effects of the electron interacting with the vacuum. Feynman, along with Julian Schwinger and Shinichiro Tomonaga, developed the mathematical tools to calculate this. And when they did the calculation, it matched the measurement perfectly. The vacuum is not empty. It's a seething, fluctuating, jittering mess of quantum activity. And it affects everything. Now, here's where it gets even stranger. Let's talk about other fields. The electromagnetic field is just one field. There are other fields filling space. There's an electron field, a quark field, a neutrino field. Every type of particle has an associated field that permeates all of space. And every one of those fields is fluctuating. The vacuum is not just the electromagnetic field jittering. It's all the fields jittering simultaneously. A chaotic symphony of quantum noise happening everywhere all the time. You're sitting in your chair right now, and at every point in the space around you, electron fields are fluctuating, quark fields are fluctuating, photon fields are fluctuating. Virtual particles are popping in and out of existence. None of this is visible. None of it is directly measurable in the sense that you can point at a specific virtual particle and say, there it is. But the cumulative effect of all this activity is absolutely real. It changes the behavior of real particles. It creates forces. It affects the structure of atoms. You are immersed in a sea of quantum fluctuations. You always have been. You always will be. Every point in space, even the most isolated regions of the universe, is filled with this activity. And here's the thing Feynman emphasized over and over. This is not optional. This is not a detail you can ignore. If you want to make accurate predictions about how particles behave, you have to include the vacuum. You have to account for the fluctuations. If you don't, your calculations are wrong. The vacuum matters. Let's push this further. There's another field that's even more important, and it's one that most people have never heard of. It's called the Higgs field. The Higgs field is different from the electromagnetic field or the electron field. Those fields, when they're excited, produce particles. An excited electromagnetic field produces photons. An excited electron field produces electrons. But the Higgs field is special. Even in its lowest energy state, even in the vacuum, the Higgs field has a non-zero value. It's not fluctuating around zero. It's fluctuating around a large constant value. And that constant value fills all of space. Why does this matter? Because particles get their mass by interacting with the Higgs field. An electron has mass because it interacts with the Higgs field as it moves through space. The stronger the interaction, the more mass the particle has. Particles that don't interact with the Higgs field, like photons, have no mass. They travel at the speed of light. This is extraordinary. The reason you have mass, the reason your body resists acceleration, the reason you don't just fly off into space at the slightest touch, is because every particle in your body is constantly interacting with a field that fills all of space. The vacuum is not empty. The vacuum is a thick, pervasive field that gives everything its mass. Without the Higgs field, electrons would be massless. Atoms wouldn't exist. Chemistry wouldn't work. You wouldn't exist. The structure of the vacuum determines the structure of reality. Now, you might be thinking, okay, fine. The vacuum is filled with fields and fluctuations. But those are abstract things. They're not really there in the way a rock is there. Wrong again. The vacuum has energy, real, measurable energy, and that energy has consequences. Here's a simple way to think about it. Take a region of space, any region, a cubic meter of vacuum far from any stars or planets. That region has energy in it because of the vacuum fluctuations. Every field is fluctuating, and fluctuations carry energy. Add up all the contributions from all the fields, and you get a number. That number is the energy density of the vacuum. Now, here's the problem. When you actually try to calculate that number using quantum field theory, you get infinity. Literally. The calculation blows up. Why? Because there are fluctuations at every possible wavelength, from the size of the universe down to infinitely small scales. And each fluctuation contributes energy. Sum them all up, and you get infinite energy. This is obviously wrong. The universe doesn't have infinite energy. So what's going on? The answer is, we don't know exactly. This is one of the biggest unsolved problems in physics. We know the vacuum has energy, but we don't know how to calculate its exact value. There are tricks to get around the infinities in calculations, techniques called renormalization that Feynman helped develop. These techniques work brilliantly for making predictions about particles and forces. But they don't tell us the total energy density of the vacuum. They just tell us differences in energy, which is enough for most purposes. But cosmology cares about the total energy, because energy curves space-time. That's what general relativity tells us. Mass and energy warp the fabric of space, and that warping is what we experience as gravity. So if the vacuum has energy, it should curve space. And it does. We call this dark energy. Observations of the universe show that space is expanding. And not only that, the expansion is accelerating. Galaxies are moving apart faster and faster. The only way to explain this is if space itself has energy. Empty space has a kind of pressure, a repulsive effect that pushes things apart. We don't know what this energy is, but we know it's there. We've measured it. About 70% of the total energy content of the universe is in the form of this dark energy, this vacuum energy. The vacuum is not empty. It's the dominant component of the universe. But here's the bizarre part. When we measure how much dark energy there is, we get a number that's incredibly tiny compared to what quantum field theory predicts. If you take the quantum prediction seriously, the vacuum energy should be 10 to the 120 times larger than what we observe. That's 1 followed by 120 zeros. This is called the cosmological constant problem, and it's one of the deepest mysteries in physics. Why is the vacuum energy so much smaller than we expect? Nobody knows. Feynman knew about this problem. He didn't solve it. Nobody has. But he understood the implications. The vacuum is real. It has energy. It affects the universe. And we don't fully understand it yet. That's where physics stands. We have equations that work. We can make predictions. But the full picture is still incomplete. Let's go back to something more tangible. You're sitting in a room right now. You look around. You see walls, furniture, maybe a window. You think the space between those objects is empty. But now you know better. The space is filled with electromagnetic fields, electron fields, quark fields, the Higgs field. All of them are fluctuating. Virtual particles are popping in and out of existence. Photons are appearing and disappearing. electron-positron pairs are forming and annihilating in fractions of a second. None of this is visible, but it's happening. It's always happening. And here's the thing that should change how you see the world. Those fluctuations are not just background noise, they're essential to the structure of reality. Take the forces between particles. Electromagnetism, for an example. You've probably been told that like charges repel and opposite charges attract. But how does that work? How does one electron know another electron is nearby? The answer is virtual photons. One electron emits a virtual photon. The other electron absorbs it. The exchange of virtual photons is what creates the electromagnetic force. You might say, wait, I thought photons were particles of light. How can they create a force? Because at the quantum level, forces are not pushes and pulls in the classical sense. Forces are the result of particle exchanges. The electromagnetic force between two electrons is mediated by virtual photons that travel through the vacuum. The strong nuclear force that holds atomic nuclei together is mediated by particles called gluons. The weak nuclear force is mediated by W and Z bosons. Every force, every interaction, is the result of particles being exchanged through the vacuum. And those particles are fluctuations of fields. The vacuum is the medium through which forces act. Without the vacuum, without the fields filling space, there would be no forces. Atoms couldn't exist. Matter couldn't exist. Nothing could interact with anything else. The vacuum is not a passive void. It's the stage on which all of physics plays out. It's the substrate of reality. Feynman had a particular way of thinking about this. He developed something called Feynman diagrams, which are pictures that represent particle interactions. In a Feynman diagram, particles are lines, and interactions are points where lines meet. And the amazing thing about these diagrams is that they correspond directly to mathematical calculations. You can draw a diagram, translate it into an equation, and calculate the probability of that interaction happening. And in those diagrams, virtual particles show up everywhere. An electron moving through space is constantly emitting and reabsorbing virtual photons. A proton is constantly exchanging virtual gluons with the quarks inside it. The vacuum is full of these processes, and every one of them affects the behavior of real particles. When Feynman first introduced these diagrams, many physicists were skeptical. They seemed too simple, too pictorial. Real physics was supposed to be done with complicated equations, not cartoons. But Feynman showed that the diagrams worked. They made correct predictions. And more than that, they provided a way to visualize what was happening at the quantum level. The vacuum, in Feynman's view, was not empty. It was a buzzing hive of activity, and the diagrams showed you exactly what that activity looked like. You could see particles being created and destroyed. You could see how forces emerged from exchanges. It was a way of making the invisible visible, at least conceptually. And it changed how physicists thought about the vacuum. Here's another example of the vacuum doing work. Consider the stability of atoms. In classical physics, an electron orbiting a nucleus should radiate energy and spiral inward, collapsing into the nucleus in a fraction of a second. Atoms shouldn't be stable, but they are. Why? Quantum mechanics provides part of the answer. Electrons don't orbit like planets. They exist in specific energy states, and they can't just gradually lose energy. They have to jump from one state to another by emitting a photon. But even in quantum mechanics, there's a question. Why doesn't the electron in its lowest energy state emit a photon and drop even lower? The answer is, there is no lower state. The ground state is the ground state. The electron is stuck there. But why? Because of the vacuum. The electron is constantly interacting with vacuum fluctuations. Those fluctuations push the electron around, jitter it, prevent it from collapsing. The vacuum stabilizes the atom. Without the vacuum, without the quantum fluctuations, atoms would not exist. This is not a small detail. This is fundamental. The structure of matter depends on the structure of the vacuum. Now let's talk about something even stranger. Particle creation from the vacuum. It sounds like magic, but it's real. Under certain conditions, the vacuum can produce real particles out of nothing. The most famous example is Hawking radiation. Near a black hole, the vacuum is under extreme stress. The gravitational field is so strong that it can tear apart virtual particle pairs. Normally, a virtual particle pair, say an electron and a positron, pops into existence, exists for a brief moment, and then annihilates, disappearing back into the vacuum. But near a black hole, one particle can fall into the black hole while the other escapes. The escaping particle becomes real. It carries energy away from the black hole. The black hole loses mass. Over time, the black hole evaporates. This is purely a quantum effect. It happens because the vacuum is not empty. The fluctuations are real, and under the right conditions, they can become particles. We've never directly observed Hawking radiation because the effect is incredibly tiny for any black hole we could actually observe. But the theory is solid. It's based on well-understood principles of quantum field theory and general relativity. And it shows you just how strange the vacuum really is. The vacuum can create matter. Not from nothing exactly, but from the energy inherent in the vacuum itself. The vacuum is a reservoir of potential. It's not inert. It's active, dynamic, ready to produce particles if the conditions are right. There's another example. In very strong electric fields, the vacuum can produce electron-positron pairs. If you create an electric field strong enough, the field energy can spontaneously convert into particles. This is called Schwinger pair production, and it's been calculated using QED. The fields required are enormous, far beyond what we can currently create in a laboratory. But in principle, it's possible. The vacuum is not a barrier to creation, it's a source. This changes the entire notion of what empty means. Empty is not the absence of everything. Empty is the lowest energy state of all the fields. And that lowest energy state is not nothing. It's something. It's a specific configuration of fields with specific properties. And under the right conditions, that configuration can change. Energy can be added, particles can be created, forces can act. The vacuum is not passive. It's an actor in the drama of physics. Let's bring this back to everyday experience. You can't see the vacuum. You can't feel the fluctuations. Your senses are not equipped to detect virtual particles. But the effects are everywhere. The color of the sky, that's a result of light scattering off air molecules. But the way light interacts with those molecules depends on quantum electrodynamics, which includes vacuum effects. The stability of the atoms in your body, that's a vacuum effect. The mass of the particles that make up your body, that's the Higgs field, which fills the vacuum. Forces holding your body together, electromagnetic forces between electrons and nuclei. Those are mediated by virtual photons traveling through the vacuum. You are not separate from the vacuum. You are embedded in it. You are made possible by it. Your existence depends on the structure of empty space. That should be unsettling. It should make you rethink what reality is. We tend to think of objects as primary and space as secondary. Objects are real, space is just the background. But physics tells us the opposite. Space, the vacuum, the fields that fill it, those are primary. Objects, particles, matter, those are excitations of the fields. They're waves in the vacuum. You are a pattern of excitations in quantum fields. The vacuum is not the stage on which you exist. The vacuum is what you are made of. Feynman understood this deeply. He spent years calculating the properties of particles by summing over all possible interactions with the vacuum. He knew that every measurement, every experiment, every observation was affected by vacuum fluctuations. And he knew that most people would never grasp just how strange this is, because the strangeness is hidden. The vacuum looks empty. It feels empty. Your intuition tells you it's empty. But your intuition is wrong. Your intuition evolved to deal with objects you can see and touch. It didn't evolve to deal with quantum fields. And so you walk around with a false picture of reality in your head. You think space is nothing, and matter is something. But the truth is more subtle. Space is filled with fields. Matter is an excitation of those fields. And the line between empty space and matter is not as sharp as you think. A particle is just a localized disturbance in a field. Take the particle away, and the field is still there, fluctuating, ready to produce another particle if given enough energy. The vacuum is not empty. It's full of potential. It's a sea of possibility. Here's one more thing to blow your mind. The vacuum state is not unique. What we call the vacuum, the lowest energy state of all the fields, might not be the absolute lowest. It might just be a local minimum, a valley in the energy landscape. There could be other configurations, other vacuums with lower energy. If our vacuum is not the true lowest state, it's called a false vacuum. And if that's the case, our vacuum could decay. The fields could tunnel to the lower energy state, and when they do, all the properties of physics would change. Particles would have different masses. Forces would have different strengths. Atoms wouldn't be stable. The universe as we know it would cease to exist. This is not science fiction. This is a possibility that physicists take seriously. We don't know if our vacuum is stable or not. We don't know if there's a lower energy state waiting to be reached. But the fact that we can even ask this question shows you how far we've come from the idea that space is just empty nothingness. The vacuum has structure, it has properties, it has energy, and those properties determine everything about the universe we live in. If the vacuum were different, the laws of physics would be different. Atoms would be different. Chemistry would be different. Life might not be possible. The vacuum is not a detail, it's the foundation. So when you look up at the night sky and see the darkness between the stars, don't think of it as empty. Think of it as filled with fields, all of them fluctuating, all of them interacting, all of them creating the structure that allows stars and planets and people to exist. The vacuum is not nothing. The vacuum is the canvas on which reality is painted. And the more you understand about the vacuum, the more you realize that the universe is far stranger than it appears. Feynman spent his career exploring this strangeness. He developed the tools to calculate it, to predict it, to test it. And every test confirmed the theory. The vacuum is real. Its effects are measurable. And our understanding of it is one of the great triumphs of 20th century physics. But the work is not finished. We still don't know why the vacuum energy is so small. We still don't know if the vacuum is stable. We still don't know what dark energy really is. These are open questions. These are the frontiers. And that's what makes physics exciting. Not that we have all the answers, but that we've uncovered deeper questions. Questions that would have been unimaginable a century ago. The vacuum is not empty. It never was. It never could be. Space is not the absence of things. Space is the presence of fields. And those fields are the fabric of reality. When you understand that, when you really grasp it, everything changes. You stop seeing the world as objects floating in nothingness. You start seeing it as patterns of energy in a dynamic, fluctuating, quantum substrate. You realize that the emptiness is full. The silence is noisy. The void is alive. And that's the truth. Not comfort, not simplicity. Truth.